Hello, good morning, good evening to everyone. I would like to talk about hardware watermarking and IP metering for IP core protection today. These are some of my selected journal contributions in the area of CE hardware security from my research group. So, what is a consumer electronics hardware? So, CE product are currently composed of very highly complex DSP designs. These DSP designs are mostly core hardware accelerators from fast Fourier transforms, finite impulse response filters, and IR filters. They could either be part as a soft IP in an SOC, or they could be an independent ASIC built on FPGAs before final fabrication. So the CE hardware mainly comprises of DSP cores, blocks, and macro operators, which usually have more than 40 to 50,000 gates, and they all need security protection from the standard attacks. These IP cores from DSPs rely on high-level synthesis backbone. So here HLS is the key. So consumer electronics hardware is completely dependent on the high-level synthesis abstraction process. So HLS is a process through which we can convert an algorithm directly into its RTL counterpart with the application of several design space exploration techniques, optimization directives that help us in getting into a custom specific high performance hardware implementation. Just to give a motivation of how complex a DSP looks like, you could see a complex JPEG that we built in our lab. This is complex JPEG compression decompression IP that comprises of more than 100,000 gates. So the process of these design process of these IP cores require you to have high-level synthesis as a backbone instead of starting directly from RTL. So some examples of HLS of DSP multimedia cores could include digital filters like IIR, FIR, DCT, IDCT, FFT, and other filters, as well as some image and audio video compression algorithms like JPEG, hard wavelet transform, and many others. So here DSP cores rely on high level synthesis, and as I just said, starting from RTL or gate is not a good idea. Now let us take an example of a digital camera. Here what we could see is simply converting an analog image that is captured by CCD into digital data does not really create a digital image. So only after the image processing engine and the codec engine performs a variety of calculations on the huge amount of digital image data, we can see a complete color grayscale image. So if you could see here, the subject falls on the lens, which further goes on to the charge coupled devices which we call as CCD sensors, which produces the analog signals which we then pass through an A to D converter to produce the raw data. This raw data is then passed on to an image processing engine which is responsible for controlling the brightness, the white balance adjustment, sharpness, contrasting, and it then finally goes on to the compressing or compression engine which we call as codec, or it could then bypass it and go through TIFF format where no compression occurs to get finally stored into a memory card. Now this compression engine is usually a JPEG, which is a compressed format that we know of, and this could be an example of a DSP core. Just to talk a bit more about this, so as you know that video cameras take analog light falling on a sensor and convert it into a digital. So when you're recording a video, if the video questions aren't figured out in every 30th of a second, we start actually missing the frames. So that's why these video cameras almost have an inbuilt second processor along with the existing microprocessor, which we call as a coprocessor, which is responsible only to perform repetitive data calculations or data crunching algorithms or power hungry algorithms on that particular device. So for example, if our iPhone's main microprocessor is checking to see if we have an incoming signal or call, or we are checking if there's an email running in the background or managing the Wi-Fi. So when the video is coming through the lens, these calculations are actually handed over to the dedicated microprocessor, which we call as a digital signal processor. So for example, Nikon XP, the system on chip that includes an image processor, video processor, DSP, and a 32-bit microcontroller. An example of a DSP core in digital camera, we have the input image stored in the memory, then passes through an image blocker and splitter, then it passes through an JPEG, for 3 different colors, RGB, and then we have an image recombiner, and again we get it back into a memory. So we have a DCT, which is discrete cosine transform, responsible for converting a spatial image into a frequency image into a spatial form or time form, and then we have a quantization followed by encoding, and then again at the decompression stage we have a decoder, dequantizer, and an IDCT. In a typical C design flow, we have to start with the specification followed by the chip design process, which is integration of third-party IP cores, followed by the schematic, and finally we have a fabrication process. Now the reason for pointing these steps are each of these processes could be considered untrustworthy, especially the fabrication process and the third-party IP integration process. Now in a typical SOC lifecycle, which we start with an IP vendor followed by SOC design house, foundry, and deployment, as seen here, every step of an SOC lifecycle could be vulnerable to different types of threat. Now an IP vendor can have an inserted hardware Trojan or a hidden backdoor. The SOC design house can have problems of IP piracy, cloning. The foundry could have problems of implantation of Trojan, overproduction, and cloning. And at the deployment stage we can have problems of leakage of secret information, reverse engineering, and cloning. Each of these different forms of threats and attacks could be handled through different mechanisms, such as we can have a Trojan resistant design, we can have obfuscation, we can have low cost authentication process, we can have SCA resistant design, and several others. As evident from the graph, we could see there could be different types of counterfeiting like recycling, remarking, overproduction, cloning, forged documentation, tampering, and this is actually growing in a very rapid pace. So since 2009 this is happening at a quite rapid pace, and as we can see, the electronic companies are losing around $100 billion every year because of this counterfeiting. Now let us look at the inside of what an intellectual property core is all about. It is realized as an SOC for low power, low cost, high performance applications. So IP cores based design is used to meet the challenges, and it is often supplied by third party vendors, and the main purpose of it is to maximize design productivity and minimize the design time. In short, an IP core is a reusable unit of logic block cell layout that is developed for licensing to multiple vendors to use as building blocks in different designs. There are several issues and challenges related to security on an IP. So we have a problem of IP ownership abuse, we can have a problem of piracy, trust, protection, and Trojans. In the first type of threat model that I talk over here, we have a scenario where the 3PIP vendor carries a watermark where the attacker is the SOC integrator and buyer. In such a case, the 3PIP vendor's protection can be achieved through the hidden secret watermark, which secures its ownership. In scenario number 2, we have a watermark in 3PIP vendor, and here the attacker is in the foundry. Again, the vendor ownership can be secured, in this case using the secret watermark that has been implanted in the 3PIP. In the third scenario, the 3PIP vendor could be the attacker, and the SOC integrator could protect its design by implanting a fingerprint. So here the buyer is actually secured against the attack using the fingerprint. An IP protection or IP security can be achieved at different levels of abstraction. So we can have security algorithms implanted at the high level, behavioral level, or architecture level, We can also have it implanted at the lower abstraction levels. So these watermarking techniques, hardware metering techniques, hardware obfuscation techniques, or computational forensic engineering, which is also used for IP resolution process, can all be done or performed at different levels of abstraction. Depending on that, there could be implications on optimization, design cost, and design complexity. Watermarking for hardware IP protection usually starts with an IP core, which includes a signature of the owner embedded in an IP. So we have a watermark embedder block that takes input of the signature and the IP core and produces a watermarked IP. And again, through watermark extractor, we can extract the watermark and we can verify the presence of the signature to prove the ownership. So what are the desirable properties of a watermark? The first is it should be capable to identify the owner or creator of the design. It should be robust and difficult to remove. It should be resilient against attacks such as ghost signature and tampering. It should have minimal embedding cost to obtain the watermark design. It should incur minimal computation effort, and it should be easy to detect for an entity who has full knowledge of the signature encoding rule. So the other properties are it should be fault tolerant, that is the watermarking constraint should be distributed throughout the design, and the signature creation and detection time should be as minimal as possible. So for DSP cores or DSP hardware, implanting watermarking is best possible or optimal during high-level synthesis design process, because we are starting to design the DSP hardware right from the beginning of the abstraction level. So how it works is we have an HTML description of an IP followed by compilation and transformation. Then we perform operation scheduling, resource allocation, binding assignment, and then we apply the watermark constraint, perform the watermark constraint raised allocation process to generate the data path and controller, and finally we have a watermarked IP core. Now let us take an example. So this shows an example of digital IR Butterworth filter, and the second one shows an example of FIR filter. If we convert this into a signal flow graph, we can see with the feed forward and feedback path, this is how the IR Butterworth filter looks like. Now from this signal flow graph, we can derive the data flow graph as shown in the figure below. Similarly for FIR, we have a signal flow graph on the top, and then again we have the data flow graph of a 7th order FIR filter. In short, the process starts with scheduling of the CDFG, which is the intermediate representation of DSP based on a certain resource configuration. Then a colored interval graph is created to find out the minimum number of registers required for register allocation. Based on that, the timing or controller table is generated, and we then implant the respective signature, which has a decoded meaning in terms of the constraints, gradually into the register allocation process. Now after the hidden constraints are implanted into the DSP, we could see something like this, where we have a watermarked FIR shown as an example versus a non-watermarked FIR. Now both the figures optically look the same, however it's almost literally impossible to figure out which RTL design of a DSP contains a watermark and which does not. The red circle here shows the difference, very clinical difference between the two figures. However, we cannot make out, or an attacker cannot make out which has the watermark and which does not. This is the final synthesized RTL about to be converted into a netlist in Altera Quartus for watermarked versus non-watermarked FIR. Now there's another aspect of performing or implanting watermark is to perform a low cost watermark. Now that could be achieved using design space exploration to generate an optimal watermark. So every solution impacts the latency and hardware area in a different way, and therefore choosing a solution without performing trade-offs could affect the latency and area of the final IP design. The DSC process helps in identifying an optimal watermark solution which satisfies the user specified upper bounds of latency and area, as well as ensures a low cost solution is found. So if you look at this optimization module that is connected to a watermarking algorithm, we could see there is an input engine, and then we have a DSE engine followed by the watermarking engine. Now watermarking engine I already had discussed in the previous slides. What the DSE engine comprises of is it has a particle swarm optimization based design space exploration framework. It has an area evaluation model, and it also has an execution time model. The input engine comprises of the module library, the intermediate representation, which is a CDFG, the user constraints, and the control parameters such as swarm size, number of iterations, acceleration coefficients, and several others. So these interact with each other, and gradually over a period of time it evolves into a low cost solution for implanting a watermark. The objective function or cost function could be a graded penalty cost function in terms of the latency of the watermarked solution and the area of the watermarked solution. This is the final watermarked IP of FIR filter shown here, along with the controller and the data path, and this was the IP chipset that shows the final input output signals. There is another aspect of IP security or hardware security which is called as symmetrical IP core protection. Here inside the IP, not just the watermark or the hidden information of the vendor is implanted, but also the fingerprint of the buyer is implanted on the top of the existing watermark. So this provides symmetrical IP core protection in terms of the vendor and the buyer both. So motivation. So from an IP provider standpoint, embedding watermark is not enough to discourage piracy and unauthorized redistribution. The buyer's legal ownership of a given piece of IP must also be symmetrically protected. The IP provider desires the ability to trace a dishonest buyer from unauthorized reselling copies of an IP. It is crucial for a IP provider to distribute IPs with the same functionality but different appearance to different users. Symmetrical protection of a provider and buyer's right is afforded by fingerprinting method, where IP provider fingerprints and delivers to each buyer a unique copy of the functionally identical IP. So here the main challenge is how to implement the same IP functionality wise in many different ways to accommodate the potential IP user market. Therefore, we require fingerprinting process that can provide a number of distinct versions of a same IP core, but with a reasonable amortized design effort. Again, like a watermark, the desirable properties of a fingerprint also are same, that it has to have a low embedding cost, it should be resilient against attacks, it should be fault tolerant, it should be adaptable to any CAD tool, it should produce or provide low time for signature creation and detection, and it should preserve correctness and functionality. This paper cited at the bottom proposes a multivariable fingerprinting method during scheduling and register allocation processes of HLS in the context of DSP hardware, and it produces a very low cost, low design overhead IP protection mechanism, as well as offers high robustness, fault tolerance, and faster signature encoding decoding mechanism. So this is how the actual process looks like. We have the signature of the buyer and user. The buyer's fingerprint for IP is then decoded to produce the respective fingerprint constraints, and that goes into the HLS process along with the design inputs like constraint, library, and the application. Similarly, on the right half we have the signature of the seller, where the seller's watermark for IP is decoded into its respective watermarking constraints, and that also gets into the high level synthesis framework. Both are added on the top of each other, and then we finally have a symmetrically protected RTL design of a DSP IP with buyer fingerprint and seller watermark. Now let us look into another angle of an IP core design flow security. As we know that due to globalization of supply design chain, the possibility of intervention of attacks on IPs is on the rise. So this mandates protection of IP cores from piracy and counterfeiting, even at the earliest stage of the design flow. Now in this figure we see that the IP vendor is considered to be untrustworthy because it is coming from third-party sources. Then we have the in-house system designer and the manufacturer, which is considered to be trustworthy. However, the foundry and the manufacturer could also be considered untrustworthy in some cases. Now, in case of a third-party intellectual property code, there is a possibility of a hidden backdoor Trojan inserted without the knowledge of the SOC integrator. So what is a Trojan? It's a malicious modification of an IC or an IP. It has two major components, the trigger and the payload. It could have external activation through antennas or sensors, or internal activation through FSMs or counters. It is usually rear valued or rear triggered Trojan, and they are usually inserted inside third-party IP cores. One of the ways to tackle it is to use dual modular redundancy based scheduling design process during high-level synthesis. The process of detection purely depends on distinct vendor allocations in the original and in the duplicate versions of a DMR design. This slide shows the 4 different types of rules to achieve distinct vendor allocation procedure, and that helps in achieving distinct vendor allocation to the same hardware unit or sister hardware units from the original and the duplicate of a DMR design. This ensures that both the copies don't produce the same output, because if one component or unit comprises of a Trojan, it will produce a different output than the other. So in case of the difference, finally the comparator or voter produces or indicates that there is a Trojan inside one of the units. Now, as you could see here, as a short example of an FIR, we could see that the operation 1 and 3, which are given to V1 and V2, you could see that distinct assignments are made for operation 1 dash and 3 dash by assigning it to V2 and V1. Similarly, distinct assignments have been made to operation 2 and 4 by changing it from V1 V2 to changing it to V2 directly. So as you could see, every sister operations from the original and duplicate unit has distinct assignments. However, how you achieve the distinct assignments also dictates the final latency and area. So that has been reflected in this slide.